name is Geoffrey. I'm working with the Balash Sendroy at the Mathematics Institute in the University of Oxford. I'll be talking to you today about projective fibrations, which are got from bigraded rings in low dimension. The varieties we're not going to talk about are going to be complex varieties. And to start, the object I'm going to describe is construction. I'll give an analogy using the product of projective spaces of dimension L1 minus 1 and L2 minus 1. Product of projective spaces are constructed using a torus action on the product of punctured affine spaces of dimension dimension L1, sorry, and L2. And this sister cross sister acts, they act separately on say the factors, and the action is defined by equation 1. So subvarieties in product of projective spaces are just like in projective space are given by a bunch of polynomial. This time these are bihomogeneous polynomials of by degree di, ei. These are non-negative integers. If we fix the degree of xi and yj to be 1, 0, and 0, 1 respectively, then the coordinate ring of the product is naturally bigraded, and the bigraded pieces, say by degree d1 and d2, is given by polynomials of degree d1, tensor product of polynomials of degree d1 in xi's by polynomials of degree d2 in yi's, and the dimension is computed by simple combinatorics using the formula illustrated on the slides. Product of projective spaces come with Segre embedding. So the product sits in a projective space of dimension L1 by L2 minus 1. And the image of Segre embedding is defined by vanishing or the zeros of 2 by 2 minus of L1 by L2 matrices whose entries are given by the products of xi, yj's, where xi and yj's are the homogeneous coordinates of x and y given as a general element in the product. The image of Segre embedding is projected. We can look at this as projected in the either of the two factors, and the maps are defined. The projections are defined by either taking one of the columns of the matrices or one of the rows. And the product x1 by x2, where x1 and x2 are subvarieties of the factors, is looked at as having a Zariski topology, which is induced inside the space, projective space L1, L2 minus 1, or dimension L1 by L2 minus 1, sorry. The projection, say pi 1, when you look at this as fibered over projective space PL1 minus 1, then look at a general element in the base, then all the fibers are going to be PL2 minus 1. So pi 1 is a trivial PL2 minus 1 bundle. So for us to define scroll, we need to change the action that we seen earlier, 1, to allow the mixing of factors so that these bundles are not trivial. So before I introduce scrolls, I will fix some notations. G will be the sister cross sister, and the general element will be given by lambda mu. A lattice of co-characters omega is going to be based by chi1, chi2, where chi1 is on G is to chi2 on G will be mu. And a general action as given, and co-character of the group is based by nu1, and nu1 and nu2 are they assign parameters to nu1, for example, assign parameter lambda to lambda 1, and nu2 assigns parameter lambda to 1 lambda. And the general action is also given as defined. So lambda, omega and theta are duals to each other through checking the degree of composition of nu and chi. So what are scrolls? Take ABC, these are n tuples of integers. Then we take a lattice which is defined or generated by TIXJ, where TI are a general element, is a general element in S or bigraded. TI are is a general element in SCI0. So this is the graded piece of dimension CI of bihomogeneous coordinate CI0, and XJ is in S minus AJ BJ, and this sublattice is given by it's generated by just CI0 and minus AJ BJ. So a scroll will be defined as the quotient of CK cross CN punctured affine spaces acted on by G, where G acts. Now this time the action is defined as follows. So we split it into two. So lambda 1 acts on general element TIXJ by taking it to lambda CITI, lambda to the minus AJXJ, and 1 mu acts on a general element TIXJ and takes it to, so the first TIs are fixed, but the XJs are taken to mu BJXJ. So this action is compatible with weighted sister action on affine CK space with weights CIs. And the projection to the first factor is defined by just forgetting the fiber coordinates XJs and taking the homogeneous coordinates in TIs. The fibers are given as weighted projective spaces with weights BI. So we can summarize this in a commutative diagram where Q there is the action I've just explained, and PR1 is the projection of the first factor. The lower horizontal map is just the weighted sister action on CK. So we will call a scroll straight if the CI and BJs are all one, and we'll denote it as F with n tuples A1 up to AN. So we will say a scroll is of type N1 K minus 1 if it is fibered over PK minus 1 with the PN minus 1 bundles. A recent PhD by Marco, we studied the Calabi-Yau three-folds of Picard rank 2, which are embedded in scrolls of type 1, 3, 3, 1, and 2, 2, respectively. Gluing data on scrolls, straight scroll fibered over P1, is such that we can just look at it in an affine, in the affine covers of P1, sorry. So P1 is covered by 2 copies of C1, and the fibers Pn minus 1 are also covered by Cn minus 1. N minus 1 copies of Cn minus, of Cn, sorry. So if you look at all the 2 affine pieces, then someone can see that the scroll is covered by 2n copies of affine Cn spaces. And the gluing of this data is defined. Say, for example, if you take a chart in the fiber, say C, where CK is not 0, then the gluing data is defined by the map I've indicated down in the slides. Surface scrolls is an example that can give us why these objects are called scrolls. Surface scrolls say F with FA0 is covered by 4 copies of C2 with the gluing data that you're seeing on the slide. And then if you glue them together, I hope the pictures show how the gluing happened, then you have an object that is looking like the scroll that you know. So generally they will not, there will be some twists on this, but this is why they are called scrolls. We can also, if you're a topologist, then you have met scrolls as projective bundles, or generally in algebraic geometry, if you take a base B and a locally free sheaf, say E1 direct sum all the way up to EM, where EIs, we look at them as of rank NI with the local weights BI. Then taking the product of the sheaf of graded algebra, it will give us the scroll whose fibers are just looked at as the projectivization of the graded algebra on just a specific point in the base. These two definitions are equivalent. Someone can easily show this. A general fact is that if we change the basis, say if you take line bundles over P1 with the weights AI plus C, then the proj is going to be isomorphic to the proj when we take the proj of line bundles, the like sum with weights AIs. So this, by consequence of the equivalence of the definition, we see that scrolls by subtracting or adding some constant on all the weights AI gives us the same scroll. An example is say surface scroll F10 and is isomorphic to 2,1, F20 is isomorphic to 3,1, and so on and so forth. How do line bundles on scrolls look like? So line bundles on scroll can be seen as sheaves, a sheaf whose sections are just polynomials defined on V, which respect the action that we defined earlier. And the global sections are just seen as polynomials over Z, where Z is just the CK cross Cn punctured affine, the product of punctured affine spaces. An example is we can take line bundles, say L. So L is the line bundle associated to character 1, 0, and M will be line bundle associated to character 0, 1. So the section of L are going to be based by just the TIs, the coordinates on the base, and the section on M are defined by direct sum of polynomials of degree AJ in TIs and X product with the XJs. A general line bundle, say L chi, where chi is character D1, D2, is defined by remembering that for A given by the matrix C given, then if you multiply A by a general section, the transpose of the multi-index alpha of a general global section should be respecting, should give us D1, D2. So rearranging this with some simple gives us that of line bundle L D1, D2 are given by equation 5. So in this equation, by Q1 D2, I mean weighted partitions of D2, and the weights are fixed and they're BIs. And so think about this as the sum of BI, QIs are giving us as D2. So all such Q1 up to Qn, which gives us this sum with a fixed BI, are going to be involved in equation 5. A simple example is when we have the straight weights. This called the line D1, D2 on straight scroll is going to the sections defined by X. Linear mapping theorem is an important mapping theorem which assigns or all of the piece, and this map is defined by the map I've highlighted, and the images are vanishing of an ideal that is defined by second wage of the matrix that I've indicated there. These matrices are having blocks, and these blocks are of sizes 2 by AJs, and they are involving quadrics in these YIs. It is important to note that the second row, the first row divided by every element in the first row divided by corresponding element in the lower row respect action that or gives us a ratio T1 over T2. Someone can easily check that. And this map is going to be an embedding if all the weights AI is sensitive. An example of scroll, say F10 surface scroll, is a simple computation shows that it is a blow up of a point in P2, and the image phi M is scroll to P2. F2 is rank 3 quadric P3, and there's a special point 001 in this image, this quadric. This two quadric. So the map, the diagram you're seeing on this screen is just illustration of how F20 under the map phi M is mapped to rank 3 quadric. And because of the isomorphism that we had seen earlier, we know that scroll F10 is 2, 1, and through the map we can see the isomorphism of line bundles on scroll is based by L and M, where L and M are the line bundles that are associated to characters 1, 0, and 0, 1 respectively, as I said earlier. And we can always see that MJ, the class of MJs are defined by L and M, and all the FIs, these are the locus where TIs are zeros, are their classes are giving us L. We can prove this by just showing L is well defined, L and M are linearly independent, and also it is a non-trivial fact that all the codimension 1 subvarieties in this scroll are hypersurfaces, or by degree D1 and D2. So someone needs to show existence of such F. So intersection numbers on scrolls. So what are intersection by intersection numbers? I mean, so if we have a divisor in a variety and a curve in the variety, so the intersection of the divisor and the curve is just defined by restriction of the curve on the divisor and taking the degree, or you can define intersection through the cup product. So intersection numbers on scroll are given by the matrix I've indicated here. So it is very easy to show this because we have said earlier that L is the class of all FIs, and in this diagram you can see F1 and F2 are disjoint. So L squared is going to be 0. All the other non-trivial intersections 1 is given by seeing that all the FIs intersects MJs at exactly 1 point. So someone needs to show that M1 squared and M2 squared are having intersections minus A and A respectively. And this is easy. You just check the intersection of M1, which is minus AL plus M, and then you take intersection by itself, and then you will get these results. So how does canonical divisor of scroll computed? So this is a special line bundle which is very important in classification of these varieties and studying birational geometry of them. So canonical divisor on a scroll, straight scroll of that weight is given by the formula you see on your screens. So you take minus K, you sum all the weights AI, that will be how much the components of L are in the canonical divisor, and then minus N. N is here is the dimension of the scroll. So this is a simple computation of why this is true. I'm not going to go through it. I'm happy to explain it if someone is interested. But indeed, we confirm that for surface scrolls, the formula really is correct. It works. An example here is a fourfold scroll. So this is a scroll which is fibered over P1 with P3 fibers. So the computation shows that the canonical divisor is a line bundle associated to the character -1, -4. And a general element in the anti-canonical class is a non-singular Calabi-Yau threefold, non-singular by Bertin theorem. And further computation shows that a general fiber is also of canonical classes, canonical bundle is 0, is trivial. And from this we see that Calabi-Yau threefold fibered by family of generic non-singular aquatic K3 surfaces are the fibers of a general element X in this anti-canonical class. So this is a very interesting subject. So how does con on surface scroll look like? So if you I can see some, I can hear some sound from the background. Someone might have turned their microphone on, but I will just continue. So the characterization of effective cons on surface scroll are such that divisor D1, D2 is effective whenever D1 plus AQ1 is positive, and P1 is bounded between D2 and the maximum of either 0 or the ceiling of the fraction minus D1 over A. So looking at sections of bundles, line bundles LMN on surface scroll leads to computation of dimensions, which is indicated down there. This together with the lemma gives us a very nice diagram or table, a graph showing all the cones on the surface scroll F2, for example. So the ample cone is indicated by the red points in the lattice, the red lattice points, and the closed ample cone is the dark region. The region defined shaded by black lines, and then effective cones are defined by every point that is above the line m plus 2n is equals to 0 and m is equals to 0. So the bigraded ring associated to a scroll, general scroll associated FA, where A is given by that matrix, as a Hilbert series that is associated to it and is indicated in the middle with the equation in the middle of the slide, and a general element, a general upper surface in this scroll, a general element in the linear system of a line bundle Mn is given by as a Hilbert series associated to the quotient ring, and is given by the equation at the bottom of the slide. So the title talks about how projective fibrations are related to bigraded rings. So I will let X and H, XH, BD be polarized projective variety. H and D are line bundles on X and B respectively. And I will require that the push forward of the structure shift on X is exactly the structure shift on B. And the fibrations X to B is going to have connected fibers because of the condition that the push forward of the structure shift is exactly structure shift of B in the base. And the polarized fibers of these fibrations are polarized by restricting H to just the fibers. So if we define a line bundle LP1, P2 by taking P amount of the pullback of D and P amount of H, then this will be a divisor on X, and this leads to a bigraded ring that is indicated in your screen. And so studying this ring gives us a geometric interpretation or study of how this vibration look like. Yeah, so I can explain this more further for someone who is interested in understanding how, for example, the sections on the base are exactly the section upstairs when you look at the weight P1, sorry, the character P10. So this setup is the main setup in my work. We have that, so this setup explains that the fibrations XB are embedded in scrolls, which are fibered over weighted projective spaces. This S is just the extension of the polynomial ring in TIs by XJs. And an example here would be weighted Grassmannian fibrations. So weighted Grassmannian fibrations, say, I've slightly changed the name from FA to GA. And that's why I'll be explaining, because the fibers here are no longer Pn-1, but are weighted Grassmannian. So weighted Grassmannian are defined as the quotient, the sister action on affine Grassmannians. Affine Grassmannians are just the, are defined by Pfaffians of skew symmetric matrices. And if we take the weight W, say, on C4, then this will give us the weights on the variables xij's, and using this we can define a scroll, quote unquote. I'm quoting it because this time I'm not going to take a product of affine spaces quotient by a torus action, but I'll replace one of the factors by a con over Grassmann and say 2, 4, and I take away some closed locus, and I assign that this action will be defined by this matrix of weights, and this will give us a fibration which is having weighted Grassmannians as the fibers, and a general fiber here are going to be just hypersurfaces. So in this case, if I take a general element in the anticanonical class, then this will be a Calabi-Yau variety fibered over K3 hypersurfaces. So I also in the abstract said that I will give an informal reason as to why someone will be interested in this kind of subject. So this lies in the connection between the study of Calabi-Yau threefolds and also other classes of varieties with physics. So in physics, subject called string theory, it's said that fundamental objects in physics are not atoms or particles, but instead they are strings that move in 10-dimensional real space. That is space, time, and a Calabi-Yau, 6-dimensional Calabi-Yau variety. An example is a quintic threefold. So if it is known from mirror symmetry, a broad branch of algebraic geometry, that whenever two Calabi-Yau varieties are related, then they have the same physics on them. So this has led to answering several enumerative geometry questions from using techniques from physics. So it is important to note, therefore, that classifying Calabi-Yau threefold is an important subject in helping unravel the main secrets of the universe. Thank you for your attendance and listening. So the diagram in the last slide there shows how our particular scroll is mapped using the map phi m to a quadric of rank 3. Thank you.